Welcome to Mindful Journey. Today, we will talk about how our Earth was formed. Our story begins billions of years ago, long before the existence of our Sun, Earth, or even our galaxy. Imagine a vast, cold, and dark expanse, filled with nothing but drifting clouds of gas and dust. This is the canvas upon which the universe paints its most spectacular masterpieces: stars, planets, and the very elements that make up our bodies. These seemingly insignificant clouds, scattered across the cosmos, hold the key to our existence. They are the remnants of long-dead stars, their outer layers cast off into the void, carrying within them the building blocks of life. It is within these cosmic nurseries that gravity, the architect of the universe, begins its work. Slowly but surely, gravity draws these particles together. Over eons, these particles clump and cluster, their individual movements giving way to a collective waltz. As more and more material is pulled in, the cloud begins to spin, faster and faster, like a skater drawing in their arms. This swirling mass of gas and dust, a cosmic maelstrom in its infancy, is a solar nebula, the birthplace of our solar system. And within its depths, a star, our Sun, is about to ignite, setting the stage for the awe-inspiring journey of our planet. At the heart of this swirling nebula, pressure and heat skyrocketed. The once frigid cloud now blazed with the energy of a million suns as hydrogen atoms, crushed under unimaginable force, fused into helium. This inferno marked the birth of our Sun, a star that would bathe our corner of the universe in light and warmth for billions of years to come. As our newborn sun blazed to life, it unleashed a torrent of energy, a solar wind that sculpted the surrounding nebula. This wind pushed lighter elements like hydrogen and helium further out, while heavier elements like iron and silicon remained closer in. This cosmic segregation would have profound implications for the planets about to form. Within the disk, dust grains, remnants of long-gone stars, served as seeds for planet formation. These tiny particles, bombarded by the constant stream of atoms and molecules within the nebula, began to stick together, a process known as accretion. Like cosmic snowflakes, these clumps grew larger and larger over time. As these clumps grew, their gravitational pull intensified, drawing in even more material from the surrounding nebula. These growing bodies, now kilometer-sized objects called planetesimals, marked the first step in Earth's epic journey from dust to a life-sustaining world. The early solar system was a chaotic and violent place, a cosmic shooting gallery where collisions were not the exception but the rule. Planetesimals, driven by gravity and their own inertia, careened through the solar system, smashing into each other with ferocious energy. Some collisions were catastrophic, shattering planetesimals into countless fragments that would eventually be swept up by other growing bodies. But many collisions were constructive, with planetesimals merging and growing larger with each impact. Like a cosmic jigsaw puzzle, our planet began to take shape. In the inner solar system, closer to the Sun, temperatures were scorching. The intense heat vaporized lighter elements, leaving behind a population of rocky and metallic planetesimals. These planetesimals would go on to form the inner terrestrial planets: Mercury, Venus, Earth, and Mars. Further out, beyond the frost line, where temperatures were frigid, a different kind of planet formed. Here, icy planetesimals, rich in volatile compounds like water and methane, coalesced into the gas giants we know today: Jupiter, Saturn, Uranus, and Neptune. As Earth continued to grow, its gravitational pull intensified, pulling in even more planetesimals. These impacts, some of them colossal, released tremendous amounts of energy, heating the young planet to an inferno. Earth's surface transformed into a magma ocean, a seething cauldron of molten rock. Deep within this molten mass, gravity pulled the densest elements, primarily iron and nickel, towards the center. This segregation of materials formed Earth's core, a sphere of solid iron surrounded by a liquid outer core. This metallic heart would play a crucial role in shaping Earth's magnetic field, a protective shield against the sun's harmful radiation. Above the core, lighter elements like silicon, oxygen, and magnesium rose to the surface, forming Earth's crust. This process of differentiation, driven by gravity and the intense heat of the early Earth, laid the foundation for our planet's layered structure. As Earth cooled, its fiery surface began to solidify, forming the first solid rocks. This marked a pivotal moment in our planet's evolution, the transition from a molten inferno to a solid, albeit still extremely hostile world. Around this time, a cataclysmic event occurred that would forever alter the destiny of our planet. A Mars-sized object, which astronomers have named Theia, slammed into the young Earth with unimaginable force. The impact sent shock waves rippling through the solar system, ejecting vast amounts of debris into space. This debris, a mixture of molten rock and vaporized material from both Earth and Theia, coalesced in orbit around our planet. Over time, this ring of debris, bound by gravity, clumped together, eventually forming our moon. The moon's formation had profound implications for life on Earth. Its gravitational pull stabilized Earth's rotation, preventing chaotic wobbles that would have made our planet's climate far less hospitable. The moon also played a crucial role in the evolution of tides, creating rhythmic cycles that influenced the development of life in Earth's oceans. The scars of this ancient collision are still visible today. The moon's relatively small size and lack of a large iron core are evidence of its violent birth. And the tilted axis of Earth's rotation, responsible for our seasons, is a lasting reminder of this ancient cosmic encounter. In the aftermath of the moon-forming impact, Earth was a hellish landscape, its surface a sea of molten rock churned with volcanic activity. Volcanoes spewed forth lava, ash and gases, painting the sky in hues of orange, red and black. As Earth continued to cool, its surface began to solidify, forming the first continents. These early landmasses were small and fragmented, constantly reshaped by volcanic eruptions and the relentless bombardment of asteroids and comets. The early atmosphere was a toxic cocktail, devoid of free oxygen and rich in carbon dioxide, nitrogen, and water vapor. These gases, released from Earth's interior through volcanic eruptions, created a thick, suffocating blanket that trapped heat, contributing to the planet's extreme temperatures. Despite the harsh conditions, the stage was set for the next chapter in Earth's evolution, the formation of oceans, the cradle of life. As Earth cooled further, the water vapor in the atmosphere began to condense. Torrential rains lashed the planet's surface, filling the first basins and depressions with liquid water. These early oceans, initially acidic and hot, would become the crucible for life. The formation of oceans had a dramatic impact on Earth's atmosphere. Carbon dioxide, a potent greenhouse gas, dissolved into the oceans, where it reacted with rocks and minerals to form carbonate rocks. This process, known as the carbonate-silicate cycle, gradually removed carbon dioxide from the atmosphere, cooling the planet and paving the way for a more hospitable climate. While carbon dioxide was being sequestered in rocks, another gas, nitrogen, began to accumulate in the atmosphere. Nitrogen, a relatively inert gas, provided a stable backdrop for the eventual rise of oxygen. These early oceans, teeming with dissolved minerals and bathed in sunlight, provided the perfect conditions for the emergence of life. The story of how life arose from the primordial soup remains one of science's greatest mysteries. However, we know that around 3.5 billion years ago, in the depths of Earth's early oceans, life emerged. These first life forms were simple, single-celled organisms, but they possessed the remarkable ability to harness energy from their environment and replicate themselves. These early microbes, through photosynthesis, began to release oxygen into the atmosphere, slowly transforming Earth's toxic air into the breathable atmosphere we enjoy today. Over billions of years, life diversified and evolved, from single-celled organisms to multicellular plants and animals. Life colonized Earth's oceans, its landmasses, and even its skies, shaping and transforming the planet in the process. From the Cambrian explosion, a period of rapid diversification of life, to the reign of the dinosaurs, to the rise of mammals, and eventually humans, life has been a constant force of change on Earth. While life was evolving and diversifying, Earth's continents were on the move. Driven by convection currents in the mantle, the layer beneath Earth's crust, the continents have been engaged in a slow but relentless dance for billions of years. This dance of continents, known as plate tectonics, has shaped Earth's surface, creating mountain ranges, ocean basins, and vast plains. The collision of continents has thrust up the Himalayas, while the separation of continents has formed the Atlantic Ocean. Plate tectonics has also played a crucial role in regulating Earth's climate over geological timescales. The movement of continents influences ocean currents and the distribution of heat around the planet, contributing to the long-term stability of Earth's climate. This constant reshaping of Earth's surface has had a profound impact on the evolution of life. The separation and collision of continents have isolated populations of organisms, driving speciation and the diversity of life on Earth. Today, Earth faces new challenges, many of them brought about by human activity. Climate change, driven by the release of greenhouse gases into the atmosphere, poses a significant threat to Earth's delicate climate balance. However, Earth has a remarkable capacity for resilience and change. Over its long history, our planet has endured asteroid impacts, volcanic eruptions, and ice ages, yet life has persisted and flourished. The future of Earth is inextricably linked to our own actions. As stewards of this planet, we have a responsibility to understand the forces that shape our world and to make choices that ensure the well-being of both humanity and the countless other species with whom we share this planet. By understanding the interconnectedness of Earth systems and the long view of geological time, we can make informed decisions that ensure a vibrant and thriving planet for generations to come. From a cosmic perspective, Earth is but a tiny speck of dust orbiting an ordinary star in a vast and ancient universe. Yet, despite its insignificance in the grand scheme of things, our planet is a remarkable oasis teeming with life and beauty. Earth's journey from a swirling cloud of dust to the life-sustaining world we call home is a testament to the power of the universe's fundamental forces. It is a story of cosmic collisions, fiery beginnings, and the slow, patient work of evolution. As we gaze out at the night sky, we are reminded of our place in the universe. We are products of these stars, our very atoms forged in the hearts of long-dead suns. And as we continue to explore the cosmos, we carry with us the legacy of Earth's epic journey, the journey that continues to unfold even today.